Refraction means that light, as it travels through different media, takes different paths. So actually, this person's body is right below his head, but it looks like it's shifted off to the side because of how light bends when it goes through water. So, refraction. These are all examples of refraction. And I want you to, in each picture, think of what the new medium is. In the picture, the water droplet, the new medium the light travels through is water. With our polar bear, his body is right below his head, and water is the medium. But what about this bendy picture right here? What do you think the medium for that is? Panoramic. They use a lens. Lenses are also good examples of refraction because they're made of a new material, and when light goes through them, they bend. So, new definition for you: refraction. Refraction is when light hits a new medium. Since it hits the medium at an angle, it changes speed, direction, and wavelength. This is why, like, if you've seen the straws in a cup, if you've seen things in aquariums look distorted, right? All those sorts of things are refraction, and you can tell because there's a change in medium. The change in medium causes the change in direction, and it makes the light traveling through just air look different than the light that travels through air plus water combined. Right? Okay, neat thing. Your eye works on refraction. So you know how your eye has like all sorts of fluids in there? Kind of gross. It does. Your eye actually has 3 different areas that do refraction. And because of its geometry, it actually uses refraction to focus light on the back of your retina, where we have a bunch of cells that will pick up that light. It's refraction because the medium in your eye is different than air. Actually, the medium in your eye is going to be really similar to the demo I'm going to show us in a second. So then, in order to get refraction, you need 3 things. I need a new medium. It can't just be like a room full of air. I need air and something. It must hit at an angle. The angle thing I can explain pretty straightforward. If you look at a regular window, those are all light rays that hit perpendicular to the window. They're traveling straight from the window to your eye with no bending in between. If it doesn't hit at an angle, the light just goes through in a straight line. So I need to hit at an angle in order to see distortion. That's why sometimes if you have really thickly paneled glass and you look from an angle, you can get images that look distorted. But on normal windows, it just looks like outside. Finally, it must change speed. Light either has to slow down or speed up when it reaches the new material. If the 2 items have the same speed, then you don't get refraction, and weird things happen. So, for refraction, I need a new medium with a new speed and an angle. I need those 3 things. And when I get those things, light bends, changing its speed, direction, and wavelength. All right. Okay, so let's take refraction and look at what happens if you don't get those 3. Okay, both of these 2 pictures, we have glass, like a glass tube, right, that's inside a glass container filled with fluid. Both of these have the same glass piece in the center, but the one on the left doesn't meet the refraction requirements. So even though there's a glass tube in the picture on the left, you can't see it. Now, for the kids here, I have a thing I can pass around to show you this. What's going on is that the glass tube and the liquid that's in the sample on the left have the same speed. We have a glass test tube inside a thing that's made of oil. Wherever the oil is, the oil and the glass have the same speed of light, so you can't see the edges of the beaker at all. If you guys could take this and pass it on. Now, while that's going around, Why that is you and I can only sometimes see transparent objects. So if you think like water, glass, um, oils, things like this, we can see transparent objects because you get refraction around the edges. So if I were looking at this glass, I can see the edge where the glass meets the air. I can see the edge where the water meets the air. But I can't see anything in the middle. Transparent objects are transparent because they have the different speed of light than the medium around them. And that means that I can only see the edges where refraction occurs. Refraction allows us to see objects that would otherwise be transparent. So I can see the glass-air boundary. I can see the water-air boundary. I can see the glass-water boundary. I can see boundaries because those are the places where light bends. And since the light is bending away from your eyes, that looks dark instead of light. Okay, so then let us see. We know that things that have the same speed look invisible within each other. So if I have something like glass and oil, they have the same speed of light as the medium around them, so we can't see them. So invisible objects occur when the two objects have the same speed. Now, you and I can't do this for like humans. I can't put a material around you that would like shield you and make you invisible.
You see the edges of the beads? Oh wait, you can't.
Right. So in this case, I can't see the edges of the glass. Even though this glass rod goes all the way through the oil, I can't see the edges of the glass because they have the same speed. So they don't refract and they don't make that dim outline. So for instance, with this like physics toy here, you can see the plastic glass interface. You can see the glass air. No, you can see all the interfaces because there's changing speeds, right? Because there's changing speeds, you can see the interfaces. If they don't change speeds, then you can't see them at all. It's like they're not even there. Oh, some of them I started putting away because it's almost the end of the year. All right, so invisible objects we can't see because they have the same speed of light as the medium around them. So this comes to a new symbol. New symbol, new quantity. This symbol is N, the index of refraction. So if I know that like certain materials are invisible because they match the speed of light of material around them, we're going to use this index of refraction as a way of saying like, all right, what's shorthand for its speed? Index of refraction is some number between 1 and 2.4. Think of it as a rating. It tells you like how much slower is light in this material than it is in a vacuum. So if it's an index of 1, that means your speed of light is very quick. That's air and a vacuum. Since air has very few particles in the way, its speed of light is almost the same as a vacuum. But ice and water have a higher index because there's more particles in the way, so light slows down. Okay, things to know about this. This is a unitless value. It has no units. But I do know the larger the number, the more dense the material, the slower the light. So glycerin on this list is the slowest speed of light. Light slows down significantly when it gets into glycerin compared to air or ice. A thing you should know, but I'm not going to put on the test. This index actually changes for different parts of the spectrum. So for you and I, our index of refraction for radio waves is 1. Radio waves go through us like we're air, like we're not there at all, which kind of disturbs me. Like I would like to think at least my bones are pretty solid, but nope, we are completely invisible to radio waves. We don't distort their path at all. They go through us like we're air, like we're not even there. So whenever you and I see index of refraction,
Hang on a second.
hold on, assume it's for visible light.
How do waves longer than UV, which get stopped at our skin, go through?
Radio waves are actually much, much longer. Radio waves are the largest electromagnetic waves, largest
Yeah.
wavelength. Think like their wavelength is so big, they don't interact with our little tiny particles,
Oh.
right? Think their wavelength is so big that like their transverse, like crests and troughs, could completely miss a person. So it does depend on part of the spectrum, but just assume we're talking about visible light. Like that's what we see, so that's what we care about. Which gives us a new equation. This equation says that index number is 3 times 10 to the 8th divided by your speed inside the material. So I've had people write it like this before. They're like, okay, well, that's too many letters. What if you just put in like 3 times 10 to the 8th for C? Both of those equations are true, whichever one is easiest for you to figure out, right? On homework 10.2 and on homework 10.3, those are listed on the back page, so you don't have to memorize these equations. You can just find them on the back page of the homework. So for instance, if I wanted to find the speed of light in water, I would pick N for water and solve for V material. V mat stands for the speed of light in a material. So how do we calculate the speed of light when it's not in a vacuum? What we do is we take our little index chart, look up the material. So water's index is 1.33. Oh, and fun fact, so are the Orbeez. Orbeez speed of light is also going to be the same value. You take your 1.33, substitute in for N, and solve for V material. Notice in this case, the speed of light in water, it's slower than it is in a vacuum, but that's still really, really fast, right? That still goes around the Earth multiple times per second fast. Still a really big number. When you're dealing with these, your index is going to be some number between 1 and about 2.4. 2.4 is a diamond. It's like really, really dense, so it really slows down the light. All right. Then the 1 would be like an air or a vacuum that barely slows it down. Yeah. Okay. The cool thing about the shininess of a diamond is that because it's so dense, when it refracts the light, it can refract it off all the different little cuts. In fact, jewelers, when they cut diamonds, cut them in specific ways to make the light bounce around a bunch of times on the inside. So if you look at a diamond, it'll actually look like little rainbows in parts. And they do that on purpose because diamonds are dense, so they refract the light a lot. And then with the extra reflections off the inside surfaces, you can see lots of little rainbows. It looks shiny and people like shiny. So if you look at this index of refraction, notice that vacuum and air have very low indices. But things like rubies and zircon is like a cubic zirconia, fake diamond, and real diamonds all have really high density, high index. Because think of it as like when your density is high, there's more particles for the light to interact with, so it slows those down. In the end, the relationship you should know is that if index is large, speed is small. Now that speed is the speed in a material. The speed in a vacuum stays constant. So the inverse relationship is index goes up, speed goes down, but the speed of light in a vacuum is all the same number. So what I want us to do is I want us to go try these problems on our own for a second. How about we give you like 15 minutes or so, maybe less. They're really fast. If you turn to 10.3, it's currently in both Classroom and Drive. If you turn to 10.3, I want you to try the problems on the first page. Just the first page.